So what I'm going to just take you through, I suppose I ought to tell you a little bit about my career. I don't have any slides on my career background, but I graduated from the University of Wales in 1981. It really was as long ago as that, with a degree in statistics. And then I went to work for the Dunlop Tyre Company in Birmingham, and I started my PhD with them, trying to work out how to make tyres more reliable. I finished my PhD when I moved to the Ford Motor Company in the mid-80s. And in fact, many of the examples, not all, but most of the examples I've got this afternoon come from my time at the Ford Motor Company. So mostly it's all about cars and all the engineering that goes into a car. So I thought I would start with the definition of engineering. There's a lot of definitions out there. This particular one actually comes from, the source is the Accreditation Board for Engineering and Technology in the United States, actually. So I'll read it out because it's worth just sort of highlighting it. Engineering is the profession in which a knowledge of the mathematical and natural sciences gained by study, experience and practice is applied with judgment to develop ways to utilize economically the materials and forces of nature for the benefit of mankind. I like that definition because it talks about the interplay between induction and deduction, which of course is at the heart of the scientific method. So this graphic that I've sketched here is just, this is a modification actually of a graphic that George Box published in a paper called Science and Statistics. I've slightly modified it. On Box's paper, these two lines were parallel, but I rather think they need to converge to the solution of the problem that you're working on. So the idea here is you iterate between data and theory. So when you move from data to theory, that's inductive inference. And when you move from theory to data, that's deductive inference. And most problems don't just rely on one of those types of inference. You typically have to iterate between the two. So you can't solve every problem just by going from data to theory, which you could argue is the main activity of statistics there. And you can't solve every problem by just deducing what you think you know from the theory that you may or may not understand. So typically what you're doing is iterating between the two. And I've called this creativity with convergence, and I've called it that for a reason, because if creativity is left to its own devices unchecked, it will diverge, which is exactly not what you want if you're working in a business, for example. You need the activity to converge. So this leads me to think about what the role, or it led me to think about what role statistics should play in scientific investigations. We need to encourage creativity, so we need that, but the challenge is if we let it go unchecked when we're trying to solve problems, it's highly likely that the activity of work will diverge. So it seems to me that what we want statistics to do is to encourage creativity of the investigating team, but also to ensure that the process converges. And that's where I think where statistics comes in. We have the tools that allow problem investigations to converge to a solution. But of course context is very important here. I work in engineering, but if you think about the other activities that we do for the benefit of mankind, you know, as human beings, we quite like to disrupt the state of nature to improve things for the future. And I guess the other areas of activity where that's also true is agriculture and medicine. But of course, the context of engineering is very different from those two areas of application for all sorts of reasons. I mean, in agriculture, you have to wait for the planet to orbit the sun before you can collect some data often. And medicine, of course, you have ethics. I mean, you have ethics in engineering too, but obviously in medicine it's probably much more focused than in engineering. The good thing about engineering, I think, apart from the fact that it's fun, and hopefully my case studies will persuade you that it is that you can do experiments quite quickly. So what that does is it frees up our ability to be quite adventurous in some of the statistics we can apply. Because we can confirm the results of hypotheses quite quickly, because we can do tests quickly, and we can often get away with small sample sizes because we can rely on quite a lot of the theory of the natural sciences, for example. I want to talk about a few case studies with regard to a set of engineering variables. This is a model that seems to fit many. Is it easier if I use my, you can see the mouse, right? It's probably a bit easier, so then I don't have to turn around. So I thought I'd set up some of these examples or case studies by looking at some engineering variables which seem to be fairly universal as you go from problem to problem. This is a particular diagram which illustrates that most engineering designs, or think of this as a machine, basically machines have to have an input and they deliver an output that ideally you want. Those are the green arrows. So the input will either be a measurement of material or energy or information. Those are the three quantities in engineering machines that we can measure as inputs. And the good thing about those quantities is they're conserved. So whatever you put in, you'll get out in some form or other. So material can't just disappear and energy can't just disappear. So if you don't get the energy or the material or the information in the state that you require, which I'm calling the ideal output here, then it must be in some sort of error output, which we'll think of as failure modes, if you will. So if you find that your input to output translation isn't conserved, because you're measuring a conserved quantity, the missing material or energy must have gone somewhere. And if you can find out where it's gone, that's the indication that you've got a problem. And this is, so what we're trying to do here is maximize the ideal output, which I've called Y sub S, at the expense of the error output, which I've called Y sub Z. And Y sub Z is a function of the so-called noise variables. These are variables in the field of operation that the engineer can't deal with. Things like how the customer chooses to use the machine, for example, or how much variability is induced in the way the machine is made when it's being produced in the factory. So there's a whole category of these noise variables that we'll just call Z as a general label for them. And what we're trying to do is maximize Y sub S, the output that you want, at the expense of the output that you don't want, in spite of the noises trying to disrupt that flow. And this is really an area that we call robust engineering design, and it has its genesis in a lot of work that went on or became known to us in Western industries in the early 80s, just after I started my industrial career, as it happened. In fact, I think Shirley mentioned Taguchi on one of her slides. He was the main person, I guess, that we came across that encouraged us to think this way. So basically, it's a design strategy to improve reliability through trying to avoid these failure modes. In actual fact, this has led us to develop a theory of reliability that doesn't require measuring reliability as a probability. So if you pick up a lot of textbooks on engineering, on reliability, you'll find that many authors define reliability as the probability that the machine will fail under certain operating conditions. But in this formulation, we don't need to use probability to define reliability, because what we want to do is minimize the error output, as I've called it here, minimize the error output and maximize the ideal output. And if I minimize one, I must maximize the other, because the quantities I'm measuring are conserved. Now you can see how, so we've got design we've got design these are the things that we can embed into the engineering design to make the thing work. So there are different types of variables on this picture. I think I've verbalized some of them already. So design variables, you've usually got several of these. We'll call those X. So things like the lengths, the mass, the material properties, all the things that the engineers can change. We've got noise variables, as I've mentioned. There's usually several of these also. For example, ambient temperature, manufacturing variability, the way the customer uses the machine in the field of operation. Any variability that goes on in the field of manufacture and operation is post the engineering work, really. So they're called noise variables. The signal variable, which is this one here, there's usually just one of those. That's the energy and the material that you're putting into the system itself to make it work. And as I've already said, they're all conserved. The output variables is YS, that's the thing you want. YZ is the error output, which is what you don't want. And you can think of a simple measure of robustness, which I've not put on this slide. You could think of it as the ratio of the ideal to the error. And of course, what you're trying to do is make the error as small as possible. That's the sort of robustness equivalent to measuring reliability as a probability, if you want, which is the ratio of what's in the ideal state versus what's in the error state. So it's just another way to think about reliability. So here's a couple of pictures. And by the way, some of the statistics on these slides are fairly trivial. As I've already mentioned, I was using these in an open day when we were talking to a non-statistical audience, so forgive me if I'm teaching you to suck eggs here. What's the theory behind why does robustness work? Well, it works in a couple of ways. I mean, you can look at it mathematically, which I've done on the text box on the left here, but it's probably easier to save a bit of time if we just look at the pictures. So let's suppose, for example, you've got a graph that looks like this. In other words, you've got some control or design variable, I think I called it on the previous slide. Let's suppose you've got two values of that variable x minus and x plus. So it's a two-level experiment, a bit like Shirley's beer, but not quite as fun, possibly. So we've got two nominal values for this factor x. That's a design variable, or the thing that the engineer can control. And then we've got this noise variable z, which let's suppose for the sake of it doesn't have to be Gaussian, but let's suppose it just varies between two limits z minus and z plus for the sake of argument. So the effect of the noise factor, if you like, is given by the slope of these two lines. And of course, you will immediately recognize that as an interaction between a control variable and a noise variable, because the effect of one depends on the level of the other. So in this particular case, the effect of the noise variable depends on the level of the control variable. And if you can find something like that in your engineering system, you can exploit it. Because if your noise variable, if you set your control variable in this particular generic example to x minus, you'll transmit a lot of variability to ys, because the variability of z just transmits through the gradient of that response there. And for the control variable at the plus level, you'll see the gradient is less, so the variance that gets transmitted to ys is less. And that's exactly what we want to achieve, is low I hope that's intuitively obvious, that what we want is low variability on the output that we actually want, because then we're in a better situation of controlling what the machine is actually doing. There's another scenario we could draw. This picture on the bottom is a similar picture to this, except here we're just assuming that we have this particular response function between y and the control variable x, and in this case it's nonlinear. But the thing that both of these pictures have in common, of course, is that we're exploiting low gradients. If we can find a low gradient in the transfer function that dictates how the engineering system will work, we can exploit that to minimize the amount of variation that we see in the output that we want. That's this green image there. Let's see, do I want to see anything else about that? No, I think that's hopefully fairly clear that what we're after is low gradients. Where statistics comes in, of course, is sometimes we don't know what the underlying transfer function is. Sometimes we do. We can write it down based on, because we understand the physics well enough, but of course if we don't know the underlying transfer function, we need to determine it through doing some experiments. And in fact, some of the case studies I've got here are all based on doing statistically designed experiment to look for these gradients in the response. In fact, this example is one of my favorites because it's very simple and intuitive, but it's a simple example, but the answer turned out to be counterintuitive. This particular case was actually done in about 1957 by a fellow of the RSS, Jim Morrison, who actually only died a couple of years ago, aged 99. He nearly made it to 100, not quite. But Jim was active. Shirley and I both knew Jim very well, and he was active almost to the end, really. So he had the task of making these glass microbeads. They weren't microbeads, they were little glass tubes. He called them beads, actually, but they're really small tubes. And the idea was that these tubes had to seal an integrated circuit board. So if you can imagine, this tube is made of glass. you drop it onto the connector on the circuit board, and you fuse, the glass then fuses in the gap so that it seals the gap in the circuit board. And too much variability in the volume of the glass is a problem, because if you've got too much glass, you get this overflow here. And if you've got not enough glass, you get this gap, and that seriously affects the ability of the circuit board to work properly. But that cross-section there, that's about, if you get the glass volume about right, you get something that looks like that, where both failure modes have been avoided. So you can see this fits the model quite well. If we can get the right volume of glass in the right place, all the two failure modes in this case go away. And in actual fact, this is quite mathematically, this is quite a trivial example, because we can work out the volume of glass with this simple equation here, where d is the diameter of the bead, b is the bore diameter, and l is the length. Now, variance transmits through gradients, which is what we saw on that last picture there. So we can work out the gradients of this transfer function. We just differentiate it with respect to each of the variables, and then multiply by the amount of variance we expect around each of these quantities that make, or these measurements that make up the tube. And it turns out that if you draw the volume of glass as a function of length and diameter, for example, you get a picture that looks something like this. Now, what was really interesting about this, when Jim did this original study, it turned out that the length had the greatest variance. So to uninitiated, without any statistics or analysis here, you might say, well, in order to minimize the amount of variation that I'm seeing in the volume of this glass, I ought to attack the variation I'm seeing in the length of these beads. Turns out that's not the right thing to do, even though it's got the largest variance amongst the dimensions of the bead, or of the little tube here. If you look at the transfer function here, the visual of this equation here, what you find is the gradient in the L direction is really very shallow. So even though there's quite a lot of variation in L, reducing it significantly is not going to reduce the variation in the volume of the glass by very much. Turns out actually that the best thing to go after is the variance in the diameter. In fact, that's actually got the smallest variance of all three of these dimensions, but that's the one, because the gradient in the direction of D is very steep, that's the one that needed to be addressed. So I put that case study there just to illustrate that this idea of transmitted variation, which is at the heart of robust engineering design, even on what appears to be a trivial problem, the right answer can often be counterintuitive. And I think that's often true I don't know whether you agree, I think that's often true in statistical studies. We'll start out and do a study, and the example that people thought was going to be correct often turns out not to be when you actually get down and do the analysis. Okay, so much for glass B. I wasn't involved in that case study. I wasn't quite born in 1957. So I'm now going to migrate into some case studies I did at the Ford Motor Company. This particular example is just on an airbag, and I hope none of you have ever had the misfortune of experiencing an airbag inflate. It's quite a violent event, actually. These things inflate with nitrogen very quickly. And the task that engineers have got is to try and maximize the amount of energy that the airbag absorbs by the driver or the passenger hitting the airbag. If you can get the airbag to absorb most of the energy from the passenger, there's no energy left over to create injury. So if you can get the bag to absorb almost all of the energy, you'll minimize the injury to the passenger or the driver. So that very well fits into the model that I had before. I've just sketched. So the input variable here is the vehicle speed. The airbag then inflates, and then the ideal output, of course, is the energy absorbed by the airbag, and we can measure the G-force on the chest, for example, as a measure of that. The error output would be injuries typically to the head or to the femur. You'll often get head injuries and broken legs or ankles or something. And that if you can maximize the amount of energy that the airbag absorbs, you'll minimize the amount of energy left over to cause injury. And in fact, it turns out that when we do this experiment, that's exactly what we find. I'm just going to, these slides actually I use to teach engineers how to do experimental design. So this is a similar experiment to what Shirley had with her beer, although there's only 8 runs here, Shirley, not 16, right? This is a full factorial experiment in only 3 variables, and they're listed here. So we can change the speed that the bag inflates, we can change the size of the airbag itself, and then we can change the size of the vents in the bag. So if you just see when it inflates, there's a hole about there, because as it inflates, you want to let the air, its nitrogen. You want to let the nitrogen out so it absorbs the energy of the passenger. So this particular cube here, you've got each variable is in one dimension. So variable A is in that direction, B is in this direction, and C into the page. And the numbers in the corners represent the chest G that we measure when the passenger hits the bag. And these are often done on sled. We don't do this with real people. We instrument a mannequin and do it on those, just in case we make a mistake and screw up. You know, sometimes engineers do make mistakes and screw up. So we have careful, and that's where the ethics comes in. All right, we're not going to do these experiments on real people. We're going to use instrumented mannequins. So we can analyze the data. So, and I'm sure you've seen this way of doing it before. If any of you have read George Box's papers on how to analyze experiments, I think George Box came up in the quiz, didn't he? So we could have asked a question on this too, couldn't we? Anyway, this is the way George Box used to teach, and I was a big fan of George Box's, so I used the same. So I found this a very nice way to teach why experimental design works, because to many investigative scientists or engineers, they often find that multi-factor experiments are quite counterintuitive. They like to fix all the variables and then just vary one thing at a time, which of course we all know is a crazy thing to do. But so this is a nice way to teach. So this is the effect of the factor A, which is the speed of the bag inflation. I'm colouring it in green at the bottom there. So that's the average of the one face of the cube versus the average of the other. And we can do the same thing orthogonally to the variable B, which is the size of the airbag, and then we can do the same thing for the size of the vent. Now there are no noise factors in this particular experiment, because we're just trying to optimize the design of the. I suppose you could argue the noise factors could be the mass of the occupant, and maybe actually thinking about it, that's probably what we had. And there's an interaction, and that's what I talked about before, although here we're not talking about an interaction between a control and a noise factor, but two of the design variables. And the point I wanted to make here is I'm using colour here to teach the different contrasts that you can make in this experiment. And what I've tried to do, because I coloured B red and C, what did I colour? B was red and C was blue, I think, wasn't it? So you mix those two colours together, you get purple. So I've sketched the interaction between those two variables as purple on this, but just to highlight to people visually what we're trying to measure. So an interaction is also a measure of two contrasts in the cube here. It's not two faces though, it's two sliced squares in the cube, as you can see there. So those few slides are just a little quick illustration of some of the graphics I try to use when I teach engineers how to analyze designed experiments. Now this example is another case. I'm not going to take you through the detail of the experiment. What I've got in the graphic at the bottom is that we've done an experiment where we've got some control variables. The experiment was bigger than this. This is just a graphic to illustrate it. So we've got some control variables here, which I'm calling X. We've got the noise factor Z. Here's the diagram which shows you all the variables. So this particular example here is to try and optimize the way an internal combustion engine, which is what ICE stands for. This is very fast becoming old history, because in a few years' time, these will be illegal bits of technology in a car. And in about 30 years' time or less, everything's going to be electric and batteries. So this is a sort of history lesson, or it will be. If I do this talk again in 30 years' time, God forbid, this will be a history lesson. We inject some fuel into an engine, and what we try to do is, I'll skip some of the technical detail from the engineering standpoint. What we try to do here is optimize the fuel to air ratio just at the tip of the so the mixture of fuel to air is the mixture that we ignite, and that the mixture of the air with the fuel needs to be at a precisely optimal amount at the tip of the spark plug at the moment that the engine controller fires the plug and ignites the fuel with the air. And it turns out that if you expose this to noise like fuel quality and ambient temperature, for example, you'll find that the variation between how much fuel you inject and the fuel-to-air ratio at the tip of the plug will diverge to some extent, and what you're trying to do is minimize that divergence. So what we did in this particular case, we did a rather large experiment, much bigger than I'm illustrating here. This is just a schematic, where we were able to change some design factors, like, for example, what were the design characteristics of the fuel injector itself, and just when precisely do we ignite the mixture. We can vary the time that we fire the spark plug, and then that will change the ignition characteristics of the fuel in the cylinder. And anyway, to cut a long story short, what you're looking for a more robust design, so this is before robust engineering design and this is afterwards. So we had a situation that looked something like that ahead of time, and then after the experiment we end up with a situation like that, where we've reduced the gap between the output of the engine, this is now much more robust relative to the noise factors than it was before. The upside of all that is you get a much more efficient way in terms of the way the engine starts, and all these emissions that get emitted here, if you look at this graphic, this is all the exhaust coming out here. This is all the stuff we don't want because it's poisonous gases and whatnot. What we find is, because of the conservation principle I talked about before, the emissions, because we've optimized the ideal output, which is the fuel to air at the tip of the plug, and that mixture gets burnt, we can minimize the amount of emissions that we get out from the engine. In fact, internal combustion engines haven't yet got to the end of their development phase. There is still more we can get out of internal combustion engines, even though the industry is moving to electric now. So that was a fairly major case. It was an important study that we did at the time because we had a little bit of trouble with our engines starting in cold weather in particular. And so ambient temperature was a key noise factor that we wanted to make the engine robust to in this particular case. So let's see. So this, okay. So now this is not cars anymore. I mentioned at the beginning I was now doing some consulting. This is some work I did with Network Rail. In fact, I came in this morning from Swansea on one of these Hitachi trains. This is me in a high-vis jacket. That's not me going to Paris to protest, right? So we did it. So there's I think I can get this graphic to run. Let's see if we can get the TV to work. So so Network Rail contracted me to help them figure out, on the Great Western Main Line, which runs from Paddington to Cardiff and then through to Swansea, which is where I came from this morning. That line is going to be electrified. It won't be electrified all the way to Swansea because I think they'll run out of money, but it'll probably be electrified through to Cardiff at least. And so the challenge that I helped Network Rail figure out to try to optimize was, what tension should we put in the overhead line equipment? There's a picture here of the overhead line. I love working on the railways, and every time I see an overhead line equipment now, I spend ages just staring at it. I need to get out more, really. But
responsible for bringing it all down outside Paddington.
No, I wasn't. No, I think that was because the pantograph slipped off the contact wire and ripped out all the droppers, I think, which is one of the error states that we obviously try to avoid. So so basically you've got a contact wire and you've got a catenary wire, which is the wire that sags, and then there's a dropper off those where the contact wire is suspended. And so you can play around with all sorts of parameters on this setup. This is a computer model. So did it run through? I think it probably ran through already. Let's run it again. So this is a model of the pantograph, this structure here, and as it runs under the contact wire, it sets up an oscillation. And what you can do is, you can see on that graphic there, what you can do as an overhead line equipment engineer is you can specify what tension to put in the contact wire and in the catenary wire. And so those are just two of the variables you can play around with. You can also play around with dropper spacing, which is the droppers are the verticals that drop from the catenary down to the contact. Now, the perceived wisdom is that those droppers are equally spaced on a span of overhead line equipment. And in fact, we found after doing this study that you are better off not equally spacing them, because that encourages resonance. And it's resonance on these sorts of setups that cause pantographs to slip off the if the pantograph comes off the contact wire, it then goes on top of the contact wire, and then it rips out all the droppers, and then the electric wire. That's what happened outside Paddington. I don't know what the cause of that was, but anyway. Yeah, I'm sorry, it wasn't my... Well, there's another... other sort. So anyway, so the real upshot of this case study was you got to put your money where... As a consulting statistician, you put your money where your mouth is, right? So I did this experiment with... Here's the oscillation before we did the study, and here it is afterwards. You can see we've changed the amplitude of the oscillation, and that's what we had before we did this experiment, and that's what we had. They're on different scales, which is why the frequencies look a bit better. I just didn't have the right graphic to dump on this slide, but it's the amplitude that is the important point on that picture. So anyway, we did the experiment. I said to Network Rail, we need this tension in the contact wire, and we need this tension in the continuity wire. They'd already specified the tensions they thought they were going to use, and specified the structure in the pylons, and so it turned out they had to uproot some pylons that they'd already sunk, because they hadn't made the foundations deep enough to cope with the higher tensions that I suggested they needed. So to put my money where my mouth is, I was invited to sit in the train when we did the confirmation run, right? So I was sitting in the cab of the train while we were measuring what was going on with the... What you're trying to do with the pantograph is you need what you want to do is make the contact wire behave as much like a solid bar of metal as you possibly can, so it doesn't oscillate at all. And that's really the upshot here. So I'm sitting in the cab with all this instrumentation. They're fantastic trains, they're hopeless as a passenger. I came in this morning and the seats are so uncomfortable. But that's the train operating companies for you. I can't speak for them. This work was done with Network Rail. So anyway, the point of putting this picture on was just to show that, you know, when you're sitting in the cab doing the confirmation run and you've got all these Network Rail guys around you, and they're doing all their work now based on an experiment you designed for them, that puts p-values into context then. I don't care what the p-value is, right? Because I just want this to work. So it's very it's very important to have skin in the game, to use a horrible Australian expression. So it proves I had skin in the game, because I was actually in the cab while they were doing this test. And I'm glad to say it did confirm. I don't know why the pantograph slipped off at Paddington the other day, and I'm sorry if it did. I'll apologize. Well, it wasn't. I don't think it was. I'm going to blame the train operating company, because there is an issue here, because they think they know what the pantograph forces need to be, and it's one of the challenges is to get the Network Rail engineers to work with the train engineers so they can treat this thing as one system, and that's a huge management challenge. I wasn't in a management position here, so I couldn't help them fix that. I mean, I could have done had I have had more time, I suppose. Anyway, that's a little bit on trains, so cars and trains. So that's a big train stuff. They have a test track up in, I don't know where it is, Derbyshire somewhere. So they just lay this track out. There's about 10 miles of track that they can just play. It's like a play set, really. They do all their confirmation trials up there. Okay, we're nearly at the end now. And it's way over time. Are we okay for time? All right. I'm going to finish by 4:30 latest. Is that going to work? So back to engines again. In the automotive field, rotating components take a lot of effort, because they're the things that always fail. On rotating transmissions in engines are where most of the warranty and most of the failures happen. Getting rotating components to be robust is difficult. Anyway, this particular example was on engine mapping, so it's sort of related to the reducing the emissions on the case study I talked about a minute ago. This problem came to me early in my Ford career. So engineers were collecting... so I mentioned on that engine study, you can actually change where the spark plug actually ignites the mixture. That's called spark advance, and these are degrees before... that's before top dead center. So when the piston comes up to its top dead center of its rotation, you can choose either side of that point where to ignite the mixture. And typically we ignite the fuel before the thing gets to the top dead center. So these are spark advance degrees before top dead center. Now, and this axis here is how much power or torque that the engine is generating. And you can see there it's quite a nice smooth curve. The crosses are the actual data. Now, to an uninitiated person who knows a little bit about regression, which a lot of engineers do, you might look at that and say, I'm going to fit a quadratic. There's only one turning point, I'll just fit a quadratic. Why wouldn't you do that? Well, you can do that, but what you notice is that the data isn't symmetrical about the turning point. And of course, quadratics are symmetric about their turning point. So quite clearly, a quadratic isn't the right. In fact, you can show that by looking at the residual plot, and there it is. You see, there's definitely structure in those residuals. Okay, you can fit a time series to that if you want, but you don't really need to, do you, to see the structure? So anyway, it turns out there's a fix for this. You don't have to make the regression model too much more complicated. What you do is you fit a quadratic spline to the data, so that's what we did. And so there's a knot point there, which is very close to the optimal point for which generates the most torque. So what we've actually done there is we fitted a quadratic to the left-hand side of the knot, and then we fit a quadratic to the right-hand side. And if you do that, you get a much more friendly residual plot there. And you can, these are two sort of pictures you can show to engineers, and they get that. So they can see that this fit is obviously much better. It's not just better on an R-squared point of view, although it is, but R-squared, for example, is not the key statistic here. The key point here is, have we got patterns in the residuals? And if we haven't, then we might go with that model. Where we developed this work was we can now split this modeling into two stages. So what we first of all do is we measure torque as a function of the spark advance, and we fit some regression coefficients to this curve. And then the second stage is we take these, because we're going to do this at all sorts of different conditions in the engine. And so then what and this is written up in the literature. If anybody wants to read up in this in more detail, because I'm running out of time here, I'm happy show you where the paper is. So then in the second stage, we take the coefficients from the first stage, and they become the response for the second stage. So essentially what we do is we knit together a bunch of these spline curves to give us a surface that looks something like this at the end, and we can program the engine controller so when you put your foot on the accelerator, you're actually telling the engine controller how much air to suck into the engine, and then the computer says, well, if you're sucking in that much air, I'll squirt in this much fuel. And you can do other adjustments as well. You can actually recirculate some exhaust gases to minimize emissions and all sorts of things like that. Anyway, so you end up with a rather complicated surface that you can fit this with all sorts of numerical methods. I suppose the fashionable thing today might be some machine learning kind of thing. But anyway, that sits at the heart of your engine controller. So every time you put your foot on the accelerator in your car, the computer in the car is going back to some surface that looks like, I've lost my mouse, looks something like that, to tell the engine what to do. That particular case study was there wasn't necessarily any complicated stats there. The breakthrough there was getting the engineers to realize that by fitting polynomials, and I'm only showing one variable here, they actually had several. So people who are uninitiated to fitting empirical models to data might often default to polynomials, but in the physical world, polynomials are dangerous because they don't have asymptotes, right? And in the real world, physical systems often have asymptotes. There are limits to the performance of what you can get out of a machine before it breaks. So machines have asymptotes, but polynomials don't. So we need to be very careful about using polynomials as empirical transfer functions. And that's the main lesson from this case study, really. I think this is my last slide. You'll be pleased to know. And I've got another, this is motivated by my experience on the railway this morning. Engineers like to solve problems. If there are no problems handily available, they will create their own. And I cite the design of the Great Western Railway, the Hitachi carriages, as one such. A few failure modes that I've found coming in from Swansea. The seats are bloody uncomfortable. For 3 hours sitting on a hard seat. There's nowhere to throw away trash when you've had your cup of tea and your Kit Kat. You can't throw the trash away, you have to keep it in front of you. The PowerPoint for your iPhone is out of sight, it's on the seat, but you can't see so you're groping around trying to put your plug in. I could go on. The toilets weren't working on the train this morning. I mean, this is just bizarre. So this is why I sort of put this quote in, really. Now, engineers, they don't create problems deliberately, of course. That's a bit tongue-in-cheek. I think the real issue is that actually some of the machines that we deal with today, whether they're mobile phones or whatever, are very complicated. And I always say to engineers, there are many more ways that things can go wrong than they can go right. It's a bit like a second law of thermodynamics applied to engineering, really. If you just drift on hoping things will turn out right, they won't. It's a bit like going into a kid's bedroom, isn't it? You're almost back. You mentioned your children. I don't know whether your kids have tidy rooms or untidy rooms. The reason that children's bedrooms are untidy is there are far more untidy states than there are tidy states, right? So if you just pick a bedroom at random, it's almost bound to be untidy. And it's a bit like that with engineering. If you just drift along hoping that your new mousetrap is going to be brilliant, the chances are it won't be, because the number of ways it can go wrong far exceeds the number of ways it can go right. So my job as a consulting statistical engineer, if you like, is to, most of my work these days is actually in project management. I don't do much of this stuff anymore. When I work with my engineering clients, I spend most of my time on project management, because what I'm trying to do is get engineers to work out if they've got some problems before they get to having the problem. So that's where my sort of technical work has migrated away from sort of this technical stuff into engineering project management, and that's probably what I spend most of my consulting time on these days. And I had one more quote there. So if any of you were in Cardiff at the annual conference this year, Peter Diggle gave a nice talk when he had the Barnett Award, and Peter says, analyze the problem, not just the data, which I think is a nice way to think of it, really, and avoid type 3 errors. Do we know what type 3 errors are? We know what type 1 and type 2 errors are, don't we? Another quiz question. Type 3 errors are providing a brilliant answer to the wrong question. All right? So that's what you have to avoid.
This is from my time at Zeneca, as it then was, in Macclesfield. A customer from, what I call a customer from manufacturing, came to me and said, we have a problem with the production of, but it doesn't matter what. There's a high level of defectives in the batches, and we need your help to come up with a sampling scheme so that we can release those batches. So Andy, what level of defect is acceptable? Customer, 0, of course. Then you don't need me. Do 100% sample and reject batches with 1 or more defects. We can't do that. We'd have no product. The testing is destructive. Then you have no choice. You must specify an acceptable defect level. So when you think about classic acceptance sampling schemes, they are there in a sense to detect big problems. Drugs manufacture is covered by regulations of pharmacopoeia, but there is clearly a reliance on these defect rates, and it's what I call specification limit watching. So everything's okay if they pass the spec. It only goes wrong when they fail the spec. So this is a similar sort of example. This was a process that had been set up years before I was involved. This is the target, and it had run without problems. And now, here's the specification limit. They had problems. They were rejecting 50% of batches, and they wanted help. So the first thing, can I see the data, please? So if you look at the historic data, again, this is not exactly the real data, but it's the same. So to start with, everything was okay, and then about 1 year in, things started to drift. But they were still above the specification limit, so everything's okay, isn't it? Until, of course, they hit here, when the actual level is around about the specification limit, and so 50% of the time they pass and 50% of the time they don't. But in the intervening time, they never did anything. Well, yes, they did. They changed the production process, and that's why they started to drift. So here's another one. Broken dose units. This is a a syringe which was filled with an implant. This is for the treatment of prostate cancer, and it's injected into the stomach, and it dissolves at a constant rate, this particular one, over a month. These were manufactured in part batches of 2,500. They would take 60 of these out. They would eject the implant, and they would measure the dissolution rate, weight and content uniformity, any contaminants, and so on. And over time, there was a perception that when they ejected the implant from the syringe, there was an increase in the rate of the implant breaking as it was being ejected. Historically, about 1 in 500 would break, but they were up to about 1 in 100, so perhaps 5 times. So we can look to try and put in place some sampling scheme. Suppose that 1 in 500 is acceptable. We could start to think about what's the proportion of batches if the true defect rate is 0.21 that gives no defects in the sample that you've taken from the batch. And that's a simple hypergeometric. And it's about 90%. If you double the rate, you've still got about 80%, would still pass. So it's not a great test. And the probability of seeing 0, 1, 2, or 3, it has have those values. So if you see 1, it's not unexpected. 10% of the time you would see that, even if it's in control. So we looked at a 2-stage approach. Essentially, you would take 60, and if you saw any defects, you'd take another 60. And if you saw any more, then you'd reject. And that was a bad thing to do as well. I mean, it's not great. You're still rejecting, or you're still accepting very large proportion, even at 4 times the defect rate. So the statistical report said, we still think the 2-stage is better, doesn't have an exceptionally good operating characteristics. And then I wrote, the known relationship between the process parameter and the chance of a broken unit should be explored. The process control on the diameter. Essentially, when these things were manufactured, when the implant was manufactured, you get it's in a polymer, and they stretch the polymer out with the drug in it, and then they cut it into the appropriate length, and then that gets put into the syringe. And what was happening was they weren't controlling the diameter of the extrusion enough, sufficiently well, so that sometimes it was a slightly larger diameter, which when it went into there and it dried, because this was quite sort of sticky and at that stage, it would get attached to the inside of the syringe, and then when it was ejected, it would snap. And the trouble with it snapping, you might think, well, it doesn't matter if you put it in the stomach and it goes in and it snaps. It doesn't matter, but it does, because the surface area, the dissolution of this drug is proportional to the surface area. And if you snap one of those implants, the surface area goes up, because you've got 2 more surfaces there. So that changes the dissolution profile. So we had worked out what to do. They controlled the diameter, and what happened was the broken rate, which was 1 in 500. Oh, what's happening here? Am I going?
No, you went back.
Did I go back?
Yeah.
Okay. Essentially, the conclusion of this was the symptom is not the disease. They came to me and asked for an acceptance sampling scheme, but the real problem was the process itself. They didn't understand it. You need to understand the process as early as possible. And in fact, what happened was when they controlled that diameter, it went down from 1 in 500 to 1 in 1,200. Instead of having a scheme to accept or reject, we actually made it in such a way that probably 1 in 500 would fail, 1 in 500 batches would fail, by improving the process. How much time have I got? I'm okay. Okay, this one was the last piece of work I did for Pfizer before I left in 2006. We were appearing in front of the European Advisory Committee, the CHMP, Committee for Human Medicinal Products, and they were assessing a claim that we made that the effect of our anti-smoking drug was maintained longer than the 12 weeks that we had originally claimed. So there was an assessment report by the rapporteur and co-rapporteur, and they said comparison between treatment arms in this study can only be done at time points where the subjects have been without treatment for the same amount of time. This time window starts at week 24. Please refer to the calculations in the graph. And so they produced this graph, and it would, if you look at it, yeah, our active is no better than placebo. That is the real data from that study. Patients all receive our active. Those patients that have stopped smoking, and we test that by an objective measure by looking for nicotine in the blood. Those patients that stop smoking at this point are randomized either to placebo or to the active. So it's a randomized withdrawal design. And what you're trying to see is whether the rate of abstinence is higher on the active compared to the placebo. And the primary analysis was at this point, week 24, so 12 weeks after the re-randomization. And you'd have to say, yeah, it is, and in fact, it's statistically significant. But the rapporteur and co-rapporteur, they said, no, you can't do that because these patients, when you make that comparison, these patients have been off drug for 12 weeks. Yeah, that's the whole point of the design, whereas these are still on drug. Yes. And what they said was you have to compare them after these patients have been off drug for 12 weeks. So essentially, what they were doing was to shift the graphs, and they're comparing them at that point, having shifted everything. And of course, if you compare them, they're here. Now, our drug is doing worse than placebo, if you took their logic to its logical conclusion. So I showed them what they were doing, and in fact, my role was to go in there and say, you've got it wrong. And you've got it wrong for this reason, this reason, this reason, this reason. Now, that's not normally what we do when we go in front of a committee. In fact, the first time I went in front of one of these committees was a UK committee, and I was explaining that we'd done an analysis of log anxiety attack rates because of the distribution and blah, 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 blah. And there was an old, gnarled Scottish physician on the committee, and when I'd finished talking, he turned to me and he said, "So laddie, you're telling me that the only reason you can show your drug works is with mathematical trickery." Log transformation, mathematical trickery. But in those circumstances, if that was a scientific meeting, I'd reply with guns blazing. But of course, when you're representing the company in front of a committee like that, you have to go very gentle. The reason is, and you reiterate, and all the time he sat there going, and you get angrier and angrier, and you've got to hold it in. Now, on this occasion, we decided from the outset we would go on the attack and basically tell them they've got it all wrong. And so I said things like, well, you could make an unbiased comparison of like with like. Staggered analysis violates the purpose of randomization and the principles of controlled clinical trials, and we went through it all. And in the end, from voting 27 to 0, or whatever, 28 to 0, against us, they voted 28 to 0 in favour of us. Interestingly, at the end of this, the representative from Malta said, well, you may have persuaded us all, but it's not going to stop me smoking. We also had an expert epidemiologist who specialised in smoking cessation from University College with us, and he was even more progressive. He basically told the committee, if you don't approve this, you as a committee will be responsible for the death of at least 30,000 patients a year. I think that probably had more impact than my statistical analysis. Yes, so this was my strategy. What I should be doing is to take you through deficiencies in the report. This approach is flawed. Let me begin to explore the underlying reasons that cause this analysis to be flawed. It's flawed. It's biased. So we sort of were fairly hard hitting. Another drug development program, 2 identical trials with staggered execution. Study 1 completes and is analysed. The primary endpoint turns out to be non-significant, but the secondary was significant. So the sponsor amended the protocol of the second study, because they hadn't unblinded it yet, to make the second, what was secondary primary and what was primary secondary. And they said to me, what do you think the FDA will think? And I said, I don't think they'll like it, because you can show quite easily that by doing this, you elevate the false positive rate across the program as a whole. There was a second one which was even worse, because there were 3 secondary endpoints and they only needed 1 to be significant, and they switched them again. So that even elevates it even more. In both programs, the second trials were positive, and both applications were approved. So I said to them, the FDA won't like it, and they go to the FDA, and the FDA say, yeah, that's fine, it's okay. Despite the fact that you can show the overall type 1 error, goes up by at least 2, a factor of 2, if not, I think it was 4 or 5 in the case with multiple entries. Similar one, this is when these last two examples were when I was at university working as a consultant. This sponsor, regulatory agency A, visited first, variable X primary, not interested in variable Y, but don't mind it being a secondary. Protocol was written in line with that advice. Regulatory agency B, variable B should be primary with variable X secondary. So they went to regulatory agency B for scientific advice. And I went along. And my solution is, personally, I don't have any difficulty in interpreting all the results from a trial and coming to a conclusion whether the drug is effective or not. The agency B, their solution was the sponsor should write 2 statistical analysis plans. One for regulatory agency A and the other for regulatory agency B. And at this point, I was about to say something, and the medical director of the sponsor company kicked me under the table and essentially said, don't say anything, because they had got the result they wanted. But in reality, shouldn't the statistical analysis plan be the implementation of the protocol-specified analysis? If you say that's what you're going to do in your protocol, shouldn't you be doing it? There's an implication for the labelling of the drug in the end, and also, how are you going to report this in a journal paper? Which analysis are you going to report? And will it matter if one of them is significant and the other one isn't? Of course it will, because again, the journals will expect you to be implementing the analysis that was in the protocol. And the pre-planning prevents poor performance. I think it was Grieve's 3rd law of good consulting in a paper I wrote a long time ago. And yet, of course, in that case, they had pre-planned by the protocol being relevant for regulatory agency A, but it can fall apart, of course, if agency B has a different view. I said at the outset that the reputation of the pharmaceutical industry, and perhaps of statisticians as well, isn't always that high. And I think that we should be proud and not defensive. I think there's lots of evidence out there that the standard of clinical trials, both of the planning, the conduct, and the analysis of industry-sponsored clinical trials, is very high compared to academic trials. I think you could, if you talk to statisticians who have made their living in both environments, I think most would agree with that. And to that extent, we do important work. And if I go back to the Warwick program, this was another study from that program in which we were comparing ourselves again to amphotericin B in aspergillosis, which is a very serious fungal infection. And you can see the gain in survival. You can see how this is a very debilitating disease. I mean, mortality occurs very rapidly, or can occur very rapidly. And so getting a 13% reduction in that mortality is an important result. And as I said, we are involved in that sense in important work, and it's estimated that that drug would save 6,500 lives annually in the US. Don Marquardt, who may be well known to some of you as giving his name to a method of least squares analysis, when he was president of the American Statistical Association, the title of his talk was The Importance of Statisticians. Oops. Yes. He said there were two views. There was a narrow view in which statisticians were compilers of data, and a broader view in which we could design experiments, analyze data, develop models of prediction, and so on. And then he said the broadest view is that we should be consultancy-based statisticians. We should be identifying the statistical and information needs of customers, influencing customers to tackle problems. This, I think, is important because it says that we should be proactive, not reactive. We need to be entrepreneurial to influence our customers to tackle problems. Develop solutions to problems, not only statistical solutions. That case where I talked about with the quality control case, the problem wasn't a statistical one, it was an understanding of the manufacturing process. Influence customers to implement solutions, monitor the long-term performance of solutions. And of course it's not just in manufacturing. Equally well, it's anywhere. The RSS had a working party looking at how to monitor the performance of government schemes for whatever. When they come up with a new policy and it gets implemented, someone needs to monitor whether it's effective or not. So I tend to agree wholeheartedly with Marquardt that we do need to be more entrepreneurial. Now, it has been said by a number of people that one of the problems is that in the main, people who go into mathematics and statistics tend to be introverts. Now, of course, it's a sweeping generalization, but I certainly believe when I look at a number of my colleagues over the 45 years that I've been working as a statistician, yeah, there are a fair few that are introverted. And it's not necessarily comfortable for introverts to be doing this entrepreneurial, proactive type of role. But I do think it's essential that we do that. If you don't, you will be seen as the number cruncher in the back office, looking grey because they hardly ever see the light of day. And that's, you will have less influence than if you go out there and look to help individuals, teams, solve their real problems rather than artificial academic ones.